Hello everybody, so today I will talk about the system design of WhatsApp, and I will do these 4 topics today. Deep dives. And yesterday as a take 1, I talked about these topics, and today I will do the same. So for my own practice sake, I will try to be more concise than yesterday. Okay, so I will talk about the first one. What happens if the WebSocket connection fails? So I'm talking about this WebSocket connection. So as a quick review, when user sends a message to the server, the message is sent through this WebSocket connection to the real-time message server. And then this server sends the message to the Redis PubSub. And now Redis PubSub publishes a message to other servers, which has to receive that message for the users who were connected. And now that kind of receiver server sends a message to the user who will receiver. So that's how this WebSocket connection works in the system. And I will talk about the case when this WebSocket is dead. So there are 2 kind of situations that this WebSocket connection is disconnected. So number 1 is explicit disconnection. So the client side explicitly stops the connection, and the server can notice that the connection is terminated immediately. And the other pattern is kind of sudden disruption of the connection loss, I would say. So in this case, WebSocket connection dies without client notifies the server that it would be terminated. So in this case, what server can do to notice this connection loss is basically sending the heartbeat. So with the heartbeat, like every 10 seconds, this server can know, whether the client is still connected or not. So the server sends a ping message to the client, and then if the client even arrived, it returns a pong message, and when the pong message is arrived to the server, now server can make sure server is sure that the WebSocket is still alive. But if the pong message is not returned, server can know that the WebSocket is not dead. Okay, so in which case this sudden disruption, or is a connection loss, occurs? Let's say user uses WhatsApp in the smartphone, and he closes the tab, which is the app. In that case, typically there is no time for the client to terminate the WebSocket message. It totally depends on the specification of the app, but we cannot make it 100% sure that the explicit termination is done. Or in another case, let's say user is using the phone in the train, and the train goes into the tunnel. In that case, the WebSocket connection is lost suddenly. So it can happen. Okay, so in these cases, what happens is server deletes the dead WebSocket item from this mapping and set it. So when user, let's say, opens the app again, or when user goes out of the terminal and connected again, the WebSocket connection is built to the kind of random server again. And everything works in the same way, as I told before. So, and one more thing I would like to clarify is, so when user is back online again, and when user is connected to the server, at the moment the client hits receive parse messages API. So in this way, when the user is connected to the server, it can fetch the missing messages while he was disconnected from the server, and the client can render them in the front-end app. So that's what happens when the Websocket connection is, Websocket connection fails, and when user is connected again to the server. Now, I will talk about the second topic. What happens if Redis fails to deliver a message? So I will talk about the case when this Redis pops up is dead. So in this case, what happens is quite clear. So the messages are not delivered to the user. And what can I do? So of course we have to wait until Redis pops up comes back to arrive. But in between, what I can do is the client hits the receive parse messages API, let's say every 1 minute. So in this way, the new messages are rendered in the front end every 1 minute. So that's how the client can render the messages even if the Redis pops up is dead. Okay. And I'd like to add one more discussion here. So what if the message, let's say Redis pops up is dead only for 1 second or maybe 2 seconds, and it comes back again? So in that case, some messages are lost. And how can I notice? How the frontend can notice that message? Or I should say, let me rephrase this. With this short polling approach from the client can, backfill the missing messages every 1 minute. And of course, we cannot make it more frequent because short polling, the biggest drawback of the short polling is that server is heavy loaded with so many requests, repetitive requests. So it is not feasible to make the short polling frequency to be every 1 second. That being said, I will discuss the mechanism to notice that the client can notice that some messages are missing. More frequent than every 1 minute. So as I said, the first kind of layer to realize this is short polling. Okay. And as I said, I'd like to notice this much earlier. So I will now think of this from the user experience perspective, in which case we'd like to make sure that the message is delivered. Probably that's the case when the new message arrives. When the new message arrives, I'd like to make sure that the user can see past other messages in the same chat at the time. So I'd like to realize that. So for this, the idea is that in each chat, per chat, I add the kind of sequence number to the messages. Or I should say, per chat per user. No, it's the same. Yeah, I can do it per chat. So what I can do is add sequential sequence number to the messages in the same chat. Yeah. So what happens is that when client receives a new message, it takes a look at the sequence number and confirm that the messages with the sequence number less than that are still rendered. If not, the client hits the receive past messages API and fetch the missing messages. So that's the idea. And the problem is how I can attach the sequence number. A kind of difficulty here is that the messages in the same chat may be delivered versus sent to different server instance of real-time message service. Yeah. So what I can do is introducing the Redis distributed counter here. So this is par chat ID based next sequence number. So now, when the user receives the message here, it hits the Redis distributed counter to get the next sequence number and attach it to the message. Actually, this doesn't have to be persisted in the database. Yeah. So that's the thing. And of course, in terms of the scalability, I can make this Redis distributed counter to be Redis cluster and use the chat ID as the shared key, partition key. Because what I would like to do is keeping track of the sequence number for each chat ID, so it completely finds that, I can think of those as independent and never intersect each other, or never have to combine different chat IDs sequence numbers. So I can do the sharding with chat ID here. Okay, and yeah, that's the thing. Okay. So, but if I'd like to be more, oh, no, it's okay, yeah. So I just want to add that this sequence number may not be always the same as the order of the message.send at timestamp. I'm assuming that this message send at timestamp is created by this server. And because each server has a different clock internally, it is possible that, let's say, there is a message in server A and there's another message in server B. The send at timestamp is created A to B order, but they're almost the same time, and maybe this message B gets the earlier sequence number than message A. It is possible, but it can be accepted, because what I'd like to do here is for the client to notice the past messages which are missing. So it's completely fine that these two orders are not consistent. Okay, so, and I will add one more thing. So what happens if this Redis distributed counter goes down and dead? In that case, we can skip attaching the sequence number to the chat message. Yeah, so I will make this sequence number as the best effort. Of course, we don't want to stop the messaging feature functionality only because of this counter's server down. And in that case, the client can ignore the missing sequence number of the delivered message. And when the Redis distributed counter comes back, he can start the count from let's say what I can do is I will use some first numbers as the start timestamp of the server. So when server is booted up, I add some server start timestamp to the first part, and then I will start from 1, then 2, 3, 4. In this way, when the server is booted up again later, it is guaranteed that the sequence numbers created after that is older than the timestamps, sequence numbers which were issued before server is booted up again. Okay, so now I talked about this second layer to notice the missing messages in the client side. But there is a problem still here. There is, if the latest message is missing, the client cannot notice that. Yeah. So I will add the final layer here. So as I said before in the first discussion, this real-time message service does the heartbeat to the client to confirm that the client is still connected. So I will make use of this heartbeat connection. So now what I can do is add a sequence number to the messages in the user, per user level. So in this way, let's say here, I can use the Redis distributed counter in the same way per user. So I will show the data flow. So message is sent to the server, and server publishes the Redis pub sub, and Redis publishes a message. And immediately before sending that message to the user, I attach this receiver server issues the new sequence number for that receiver user, and attach that message to attach the sequence number to the message and deliver it to the client. So in this way, per user sequence number can be measured. And now the heartbeat process, before sending the heartbeat, it fetches the user's latest sequence number from this and attach it to the heartbeat. And now client can know until which message sequence number it has received the messages. So now if something is missing, if the client is the latest message number client had and the latest sequence number delivered by heartbeat, if they are different, the client calls receive past messages API and fetch the missing messages. Okay, so this is a mechanism how the client can notice the past missing messages. So short polling every minute, and also per chat message ID, so message sequence number, and per user message sequence number. Okay, so this is what happens if Redis fails to deliver a message temporarily, and how the client can notice the missing past messages. Okay, so the third topic, how do we handle out of order messages? So I think I should start with the definition of the order of the messages. So order of the messages is kind of tricky part here because each message is sent to different server, and each server in my design puts the timestamp sent out to each message. So because there is a small gap between the clocks, amongst the clocks of servers, I cannot guarantee the strict order of the messages. But the discussion here is, do we really need that strict message order? If we really need it, I can use the Redis distributed counter, or I should say a central server, which puts the timestamp, and this message service has to, ask the central timestamp server to know the strict order time. But obviously, we don't have to be strict on that. Yeah, of course, this central server approach has the drawbacks, like the latency, extra latency to call it, and also the central server can be the single point of failure. So I don't want to introduce that. And actually, as long as the time gap between servers are quite small, it's totally fine for each server to independently issue the timestamp. This is the product decision, but I'm almost pretty sure that it accepted in the WhatsApp app. Okay, so the thing is, each server sends a timestamp, and then in the end, the client side, after receives the message, it displays it sorts the message in the order of the sent at timestamp attached to the message and displays them in a sorted way. And specifically talking about the out of order messages, it is possible that the timestamp with message with later timestamp arrives first, and then the message with earlier timestamp arrives next. I can think of this as a kind of out of order messages, and again, this is totally the product decision, but I think it's totally fine that the message which arrived, I think it is totally acceptable that the order message is inserted before the latest message in those cases. Yeah, I think we don't have to, of course, sort them in a order of the delivery of the message in the client. For user experience perspective, it's quite annoying and the user never expected. So I think the answer of this is we don't support the out of order messages because it's better in perspective of the user experience. Okay, so I will talk about the Rust discussion topic. How can we handle Rust online add functionality? So this is a kind of, challenging topic, I can say. So I think the most kind of naive approach is when user is connected to let me firstly start with the definition of this functionality. So in the WhatsApp, I can see the list of users, my friends, and I can see if he's online, it is shown as a green small dot on the profile icon picture, and I can see if he's online or not. And if he's offline, I can see how many minutes before he was online, and or I should say how many minutes before he became offline. So That being said, what I need to sustain is, in the backend is, when the user was online last time. So kind of approach I come up with is Redis OnlineDB. So I add a new Redis, and for user, I store Rust online add. And the kind of approach is I set the TTL here, like to 1 minute or something. So when the user is connected to the WebSocket, this real-time message service periodically updates that user's Rust online add in the Redis. And then, if that is not updated, because of the TTL, let's say user isn't connected anymore. In that case, this update doesn't happen for that user ID. So that record will be deleted with TTL of the Redis. So this is now deleted after a while. And I would say I would add new server, which is the online presence server. And this can be HTTP. So user makes a request to fetch the friend's online status periodically, like every 1 minute. And then this calls the Redis online DB to fetch those users Rust online add, or if it is missing, it means he's offline. And those data are returned to the client, and client side can update the online status of his friend. So this is the kind of first approach I come up immediately. But there are some issues. So the biggest problem here is, there are two problems. Number one is the kind of overload to this server. To this Redis. And the second is the latency. So in terms of the overload, the client makes the let's just say, I think I should talk from the latency. So because we use short polling approach for each of updates the record in Redis and fetch the record in Redis, I cannot make this frequency like 1 second. As I said, short polling heavy loads the server or database so much, so it is not possible. So I have to compromise with, let's say, latency every 10 seconds or something at best, I think, or maybe every 1 minute. But when I think of this application as a real-time messaging app, 1 minute latency is very huge because the user is chatting with other users, and of course when he's chatting, he'd like to know the other user he's chatting with is online or not. So we expect that the online status change to be reflected less than 1 second or something, just like the latency for delivering some messages. So that being said, if we try to reduce the latency and make it more frequent, it means that there are more and more load on this Redis DB, so it doesn't work. Instead of that, the approach I can suggest is So every time some user becomes online or user becomes offline, I deliver those changes immediately to the client, other client. So let's say some user is connected to the server and that user's online status should be published to other users in the same way as the messages. And the problem here is who are subscribing those users' online status. So yeah, of course I can do the same way. So I would say I would call this Redis message PubSub and Redis online presence PubSub. So here in this way. So Redis message sends a real-time message. Okay, so firstly we have to define whose user's online status some user, a specific user is interested in. So I can limit this with UI. So UI, let's say UI shows only 20 other users' status, or maybe chat history. And if he scrolls down, the client will keep track, the app will keep track of many more users, additional users' online presences. So in this way, when the user opens the app, firstly, let's say the user sees only up to 20 friends online status. So when user opens the app, this client makes a request to real-time message service to clarify. Wait. I think I can separate this, Yeah, I think I can even separate the, I will delete this. So I think I can separate real-time online presence service here. So this Redis, this server, uses this. So I use the Websocket, another connection here. So when user opens the app, this sends 2 messages to this server. Number 1, this user became online. And number 2, this user is interested in 20 users' online presence. So with those, this server firstly creates the subscription to Redis presence PubSub. So I can make it one topic per one user basis. So this real-time presence service subscribes the 20 friends topics, and then because this exact user is connected, he publishes the message to the topic which corresponds to this user. And what happens is that the users who'd like to know the online presence of that user, this user, receives the online status change message and send it to the client. So now the client can display that this user became online. So this is how the online status can be, offline to online change can be published and propagated to the friends. And when I think of the opposite one, I mean online to offline status change, as I said before, this real-time presence service can notice that with the heartbeat. So this real-time presence service sends a heartbeat to the client, and if it is missing, it means that that user became offline. So now this real-time message presence service deletes that WebSocket object from the mapping and also sends the online to offline status change to the Redis presence pops up, and that message is published into other users, his friends, client through this WebSocket, and then that client device can remove the online status of this user. Yeah. So in this way, the good thing is every time online to offline, offline to online change is immediately propagated to other users. Now other users can display their it's very easy for the front end to render how many minutes ago that his friend became offline, because online to offline status has been already sent to the client. Okay, so this is it. Yeah. But I have one more thing I have to make sure. So I said when user becomes offline, this real-time presence service sends the offline change status update message to the Redis pops up. But let's say this server goes down immediately. In that case, this server of course cannot send the offline status change message to the Redis pops up. So what can I do? So for this, I should save the last online add in the end in the Redis DB. Presence DB. So this stores user ID to last online add. So I think we can use the same policy here. So because this is a kind of fallback safety net for this server going down case, I think I don't have to make it super explicit and super strict. I can just let's set the goal for the offline status to be updated within 5 minutes, maybe 3 minutes. So in that case, this real-time presence service periodically checks the WebSocket connection and updates its record, user ID to last online add record. So now, if the server goes down after 3 minutes, this record goes away. I mean, is deleted with TDL. And now this client can, periodically hit the server to fetch the online status as the safety net. So real time, this is presence service. This can be HTTP. So client side, let's say every 3 minutes, hits the presence service API and fetch the user's last online add timestamps. So in this way, if that user's online status is missing, if his friend last record is missing in the Redis DB, it means that he's offline. And the client now checks for users displayed in the UI. Each user is really online now with the mapping returned from the Redis presence service. And if there is any user which is offline, but actually the client was thinking he is online, now this client believes in the response from this presence service API and makes that use friend online status to be off. Okay, so that's how I can realize the online presence feature. Yeah, I will be quickly, review about this one. So quickly saying, instead of, online presence, or I should say, I use the WebSocket for the online presence too. And the thing is, every time user's online status changes, propagates that to his friend client devices. So this is for the low latency powers. But as I said, it is possible that the server goes down. So as the safety net, I persist uses Rust online add in the Redis, and I set the TTL here. So if this kind of heart beating online presence update doesn't occur, this Redis presence DB's record is deleted. So now client periodically, let's say every 3 minutes, hits the presence, online status bulk fetch API and checks checks that the users are really online or not. Okay, so now today I talked about these 4 topics. And actually this is the end of the WhatsApp videos. Yeah. Okay. So I finished my today's systems and practice with this. Thank you so much. Bye.